So we start this evening keynote lecture with Professor Richard Martin from the Department of Physics at the University of Illinois at Urbana and Department of Applied Physics at Stanford University. Professor Richard Martin, I think, is very well known for a lot of very inspiring papers, and very recently also for a very interesting book on this field that has been very well known for all of us. So this evening it will talk about electronic structure from the top down, predicting the behavior of material starting from high energy.
Thank you. It's really nice to be here. Thanks to the organizers, and nice to see all of you, especially people I don't know. I'm looking forward to knowing you better in the future and to your papers as well. So I made a title that was meant to say something that I would like to sort of do more myself, and would like to point you in a direction to say, let's look around and see how else we can look at the same problems. So our usual way of doing things in our community is what I'm going to call the bottom up, which is starting with the ground state. As we know, that's what density functional theory is about. And it's because of density functional theory that we can actually do something practical with ground states of real materials. And the key words, and when you start with this approach, is energy. So that'd be ordering things by energy, minimizing the energy, and order. The order means, I've already used the word order for energy, but also order in space. So the crystal structure, where the atoms are, basically. So if, with the same approach, you can calculate the elementary excitations, and there's been some nice talks on that, particularly for phonons, but also magnons. Like there's work with the Berry's phase approach for spin density waves, just like there is for phonons. The non-collinear magnetism that was talked about today is going beyond the usual spin density, but that's for getting it at basically low energy properties that are related to magnetism, displacement of atoms. Well, I'll just keep going. And as we go up in temperature, the basic idea is that we would have to involve more of these states, and we get different properties as a function of temperature. All right. So in principle, this is well understood. And in practice, of course, it's density functional theory that lets us do something. And the advantage of this, one of the many advantages, is that it's most straightforward to take nicely ordered systems in order to do these calculations. Right? And as recently we've gotten around to being able to do very complex systems without any apparent order, but still the place where we really understand it best is treating ordered systems. So if we look at it from a high temperature perspective, basically this is when the temperature is above some characteristic scale, and we want to talk about that later. Then we know that things are uncorrelated at high temperatures. And the keywords are entropy and disorder. And if you start going down in temperature, then you get more and more order in the spectrum or the types of states, and as lower temperature, you start breaking up the bound states, and they become the important parts of the problem. And from this end, we'll be talking about correlation functions, spin correlation functions, charge correlation functions. So this would be textbook material starting from high temperature, and it's textbook, right? statistical mechanics is really very much in this vein. And the sense in which I think of it as textbook is that if you go back to your textbooks, this will be just as important a piece of physics to learn as the low temperature, well, maybe not quantum mechanics. Okay, that's really important. But the ability to treat materials at low temperatures. In fact, you'll find more on statistical mechanics. Think about that. So in principle, this is well understood. And the advantage is this less correlation at high temperatures, so you should be able to do some things better at high temperatures. And there's a nice description. Now, unfortunately, I wasn't here for Walter Cohn's talk, but I saw the title, and it's this beautiful piece of work he's called nearsightedness. And since Nicola gave her opening for me to follow her and be blatantly self-promoting, I'd like to I like to think that you would recognize that, and I'd like to give a sense of which would be the way I look at it and the way I like to ask you to look at the problems. So, chapter 23, linear scaling. Actually, there's kind of references to this earlier, but these were the subtitles. Nearsightedness, and earlier in time with several people like Friedel and Heine that particularly wanted to look at properties without assuming that things were perfect crystals. And here are some little quotes from a page or two into that chapter. And it's nearsightedness is a property of many body systems. So this is not Kohn sham or some particular approximation to density functional theory. This is something that really should be true, period. If you look at the density matrix, then you can really see how it works in independent particle problems. You can get analytic formulas for it. But the density matrix as a function of distance in a real many-body interacting system is something that you can work out as well. And as you go to higher temperatures, the range gets shorter, and it should be exponential as a function of at higher temperatures. At very low temperatures, then of course things get more and more delocalized. But in insulators, and this is a part that Walter Kohn has emphasized in particular, even at zero temperature, you still have exponentially confined density matrices. So if you look at things in terms of density matrices, then you get this picture of localization. If you look at things in terms of eigenstates, they're not localized. And let me see if I've got something else on that. I'll come back to that. So this would be the picture that I would like to get you to think about as we go along. I'm not trying to get you to ignore the ground state work, because that's really, really, really useful. But let's look at some problems where you can benefit by thinking from high temperature, or benefit from just thinking about the problem in general. And of course, free energy is what's going to be in the middle of this, and it'll be the one thing that really puts it together. Okay, so the theoretical formulation is a partition function, and the free energy is as a log of the partition function. See if I can get my finger on this. So the partition function is the sum of all the states of the system weighted by the Boltzmann factor. And if you think about it as eigenstates of the system, it's this top line. If you think about it as expectation values, it's the trace of this operator. So if you start from low temperature, it looks like things just get harder and harder as you go to high temperature, because this exponential factor decreases slower and slower as you go up in energy, and you need more and more eigenstates. Okay, so I'm going to come back to this point of the difference between eigenstates and what you need to deal with to get things like a free energy. So let's take a single particle problem in a box. This could be, let's say, the lowest energy state in the conduction band of silicon. That state is spread over the entire crystal, and it's affected by the boundary conditions on the boundary. So every one of the eigenstates is extended. But if you sum over the eigenstates in some property like this partition function, or to get to the free energy, it's the sum over the eigenstates involves phases that between each of the eigenstates, so that when you sum over them, the long range part cancels, and you're left with only the shorter range part. Okay, so this is famous from many problems, and Volker Heine, whom I mentioned before, had a really good analogy. If you look at a cavity for electromagnetic waves, every eigenstate of that system depends in detail on the shape of the cavity and all its properties. But the Boltzmann-Stefan law about the radiation is just t to the fourth. Didn't matter on the precise details of the cavity. So there's lots of things that you can learn without going through enormous detail. Starting from high temperature, then apparently it gets more difficult as the temperature is lowered, because there are longer correlation links. And I think this is just fundamentally correct, and so that I think is a fundamental issue coming from high temperature. Now, what kind of temperatures should we be talking about? I like to think of nature's unit of temperature as Hartree divided by the Boltzmann constant, and that's like 200,000 Kelvin. So if we're dealing with hydrogen and what temperatures you would not only ionize, but you would essentially totally ionize hydrogen, you'd be talking about temperatures of this sort. If at much lower temperatures, though, of course, you partially ionize hydrogen, but because it's only the Boltzmann factor. But this would be a scale that you might think of for general electronic energy scales. If you go to core states, of course, if we talk about much higher energy to ionize core states. But if we look at actual valence problems in solids, the typical energies are much less than a Hartree. So we're talking about ranges that are like, say, 1 electron volt or 8,000 Kelvin for say, the band gap in a semiconductor. Okay. Notice down here, I want to ask you some questions. So there's really good reasons to ignore the effective temperature for a lot of cases. Let's go to our temperatures that we might wish to work at are just way lower than these characteristic scales. And there's some practical reasons to ignore the effective temperature for electronic excitations. So here's a question to you. I'd like a show of hands for some things. How many of you have heard of the Mermin theorem? I see a couple of hands up.
Is it different from Mermin-Wagner?
No. Okay, so I was going to explain, and then there might be some more hands come up.
Okay.
There's a Hohenberg-Kohn theorem that says that the total energy of the system, well, all the properties of the system are governed by the density, and we usually call that the density at t = 0. There's another theorem that's just as powerful and just as clear, as called the Mermin theorem. Does anybody know that now? Hands up. Oh, to you. Okay? The statement is that if you look at from the density at any temperature, you should be able to determine all the properties of the system. Not just the density at T equals 0. And the theorem works just by going through free energy and doing exactly the same logic as in the Hohenberg-Kohn theory, that Hohenberg-Kohn approach, that you want to prove that there's only one potential that could give that density at that temperature. Okay? So now you know the Berman theorem, right? Okay? Now, at least 5 or 6 hands were up. How many of you have used it? Anybody, any hands up? I'm quite sure not. Why? Why don't all of us just use it? I mean, we care about things at finite temperature. We'd like to work on the interior of Jupiter, which is 40,000 Kelvin. We'd like to know what that is. Why don't we just use it? Who knows the answer to that? A function will exist. Somebody give me an idea of why it might be that we don't use it. We don't know the function. You got it. It's really remarkable how good is the local density approximation for the ground state, right? And then the improvements on that. What would it take to have a functional that actually works at finite temperature? What would you have to have? Let's go back here, right there. Let's look at it from the perspective starting at T equals 0 and then going up in temperature where you have to have more and more of these states. One of the things you can get from the free energy is, for example, the specific heat. Okay. We know that gets renormalized in solids. And you can think of it as each one of these excitations is an excited state. If you're thinking about starting from the ground state, although it's the particular distributions of excited states is the one that gives the free energy. So this distribution of excited states has some great simplifications, but nevertheless, we should be able to get the properties like specific heat, which has renormalization from the Kohn-Sham approach. Like in an alkali metal, you get essentially a free electron parabola, but with the density of states and the specific heat gets modified. If you go to a transition metal, it can be modified very much. If you go to one of the systems like I'll mention later, it can be 1,000 times what you get out of a band calculation. And that's hard to model. Okay, so there aren't good practical ways of using such a theorem. Okay, I have another question. So why is it difficult to treat these real materials at non-zero temperature? Well, it's just difficult to carry out that trace. It's difficult to, if you look at the eigenstates, and it's difficult to make the trace. And it's basically, if you think about what you've learned in your textbooks, if you have a small number of options, small number of possible states per, say per site in a crystal, then you can actually do the calculations, and you'll wind up with something like the Ising model or Heisenberg, and you can do quantum or classical Ising, Heisenberg, etc. So I've mentioned states like that. What would be something else? This is a question to you. what would be some other cases where you might have a small number of degrees of freedom that you could use what you learned in statistical mechanics? Any ideas? It's not easy. I mean, it's really not. So I'm not surprised you don't quickly come up with ideas. Nicholas Paulding mentioned one last night, just kind of went over it quickly. Ferroelectrics. What could be a small number of states that you would care about? Small number per site, really, is what I mean. Okay? If the easiest one to think about would be the molecular ferroelectrics, with each molecule have a dipole, and they could be at high temperatures. They wouldn't have any particular orientation, but as you come down in low temperatures, the dipoles would order just like a magnet, right? And there's some very nice work doing quantum Monte Carlo or classical Monte Carlo for working in the finite temperature calculations for systems like that. Where do you get the parameters from to go into that calculation? Where do you get the parameters from? Our DFT, right? So we know we can calculate dipole moments, and we do a pretty good job. We know that the Coulomb interactions between them involve some screening, pretty good job. And we know that lattice displacements is something we do very good job on, and all these phonon frequencies and secondary minima. The ferroelectric transition itself is at zero temperature, is given quite nicely. So you can make a model of small number of possibilities for each atom or each molecule, and then do statistical mechanics on that. So starting from things that you know about, you can then generate models that essentially, this is the bottom-up approach. Things you can really calculate in some systems and then use them in others, especially at finite temperatures. And that's something you'd really like to know about. You'd like to know what's the susceptibility of a ferroelectric above its ordering temperature, or near the ordering temperature. That's very important and has to do with the device issues, even though I don't know anything about it. And there's some almost ferroelectrics that don't quite make it, but they have enormous polarizability, which is a very useful thing. Strontium titanate is one of those. Right. So that's at T equals 0, you need to be calculating something that has a lot of fluctuations in order to describe that system. Okay. So temperature is interesting, and I'm going to go over my list. So magnetism, and I'm going to call this an electronic structure problem because spins are electrons, really. That's where they come from. And if we really want to go back to basics, we're going to start with electrons and predict the properties of a magnet. So the typical scales for ordering temperatures, the Curie temperature, is very low in some systems up to of order 1,000 degrees. That would be like iron. And this sets the scale for, I should have said, ferromagnetism, to be precise, ordered magnetism or antiferromagnetism, say. But there's other scales of the problem that are basically the bandwidth, that's many electron volts, the exchange, that would be the interactions of the spin-dependent interactions in the system, or you can think of it as spin-dependent, but really it's just the Coulomb interactions inside an atom. These are big energies, and somehow you also want to get the small energy scale out. metal insulated transitions and the transition metal oxides. I'll mention a little bit more about that. There's the condo effect. This is magnetic impurities in metals, but we're going to see a case where it's not so well understood when you have a whole lattice that acts like these condo impurities. But if you look in the literature, some of the famous systems that exhibit this condo effect, which is a resistance minimum that's observed at low temperatures, it might be a millikelvin. And not so well known is that there can be others at 1,000 Kelvin. So these many-body effects can span orders and orders of magnitude, even though the basic fundamental parameters like the electronic interactions and bandwidths don't change anything like that much. I want to show you the example of cerium, where this effect can cause a huge volume change. Okay? So in every case, there are also high energy scales in addition to these low energy scales you'd like to look at. And I want to emphasize low energy scales because this is where temperature matters. It's when you get above one of these low energy scales, even though there are high energy scales in the problem. So this would be examples of types of systems where at accessible temperatures you get interesting properties that really depend on the temperature drastically. Okay. Any questions or comments just to help me and everybody else? I appreciate it. Okay, do you think as you go along, please? So if we look at the periodic table, this is now I'm coming back to what was discussed today. The first lecture by Matteo said he was going to treat open shell systems. What are those? The transition metals and the lanthanide and actinide series are where you're filling in the D states or the F states, and the chemical properties aren't changing very much as you go across because the lattice constants, the many properties are governed more by the S&P electrons and not as much by the particular filling of the D shell. That's not really quite right, but the idea is that there's a much bigger effect of the filling of the D shell, which would be have to do with the spins that are generated, and the change in magnetism as you go across this line is really quite large compared to the change in other properties. For the rare earths, they're so localized and so much atomic-like that they become easy on the other end of the scale. That just don't look at them as band-like at all, except for some interesting anomalous ones like cerium. Okay, so these elements that are basically uncolored are pretty well treated in band theory, and these elements at least have a great possibility for something that's quite different and quite interesting. So we need a method then that will treat strong correlations on the atom, which is what gives rise to the way the spins orient. For example, on manganese, you get 5 d electrons all pointed the same way. Big interactions, but small interactions between each with the different manganese. You'd like to get that as well. And do it all at the same time to get electronic spectra and things like that. So here's a slide I really like. It's reorganizing the periodic table according to localization in these partially filled shells. So it's organized with the most localized in the upper right. Is that right? More localized. I can't read it from here. That is more localized, I think. So the terbium is where the F's are most tightly bound. And in cerium, they're less tightly bound. Okay? We looked at the 3D, so that's the 4Fs, and the actinide series is less tightly bound, and you get some band-like behavior in this side and localized behavior to the right. If you look at the 3D elements, then if you go down to the 4D and 5Ds, are rather band-like and not very localized. And there's an interesting stripe across here that's meant to be a different color. That's where all the anomalous systems lie. Exaggerated, excuse me. If you just look along that line, you'll find everything has an anomaly. Cerium has this change in volume and a little bit of high pressure. It happens in neptunium and plutonium. Plutonium is really complicated. The manganese and iron and cobalt are ones that form these transition metal oxides. Copper, when you add the oxygen, make copper oxide can come into this interesting range because you've taken off the S and P electrons and you're dealing with the D electrons. So the high temperature superconductors. So things are along this line. And now we get to the point of saying, if we change the bandwidth or the interactions, it's along this line that you'll get these large changes. I'll say, I warned Nicola that I would say, last night I didn't quite agree with her. That she said, if a lot of people have asked, how do you get this value of U? How good is it? And she said, well, if you want to really predict solids, the properties of a solid solidly, if you wanted to say this is a quantitative answer, then you need to have a result that's independent of this U value to a large extent, because you don't know it that accurately. There's another class of people that would say, oh, I want ones that change a lot with U, and I'm going to look for the cases that will have transitions. And so what I would want to find, I meaning some person with this attitude, is I'm going to look for the cases where it depends a lot on you. And then you may not know it perfectly well, but you find a big change at any rate. And so I will emphasize those cases. Okay, so now what is U? U and LDA plus U, I'm not going to say much about because that's really what was talked about today. So we know that the interesting cases are when you have partially filled shells. That's what the U is doing, is stabilizing the system and one number of electrons or another number, like n or n plus 1. The density functional, this usual Cone-Sham density functional theory gives you occupations that are fractional between the energy values. And when you put in the U, it's saying it really likes to have an energy value, which is putting in some physics. But you have to identify the interesting states that actually, where that makes a difference. And in this large set of systems, they're the transition states or the lanthanides or the actinides that have partially filled D shells. That's what was talked about today. And if you want to deal with how large the effects are, you need to calculate this U as it's the screened interaction, screened by the other electrons, and that's not an easy problem. You have to identify the states, you have to calculate the U, and this is the step where you say a small number of states is interesting, and where you can do something with it, and you have all these questions of uniqueness, choosing the states, and what are these values of interactions. So everything I'll talk about later has this uncertainty about it, of just how you did it. But it'll be the same uncertainty that you'd have in an LDA plus U calculation. And so you can use some things that you know about these systems, like in the ordered antiferromagnetic state, and then take the same information and go to the disordered states at higher temperature. So you can go back and forth between high temperature and low temperature to quantify how good is the information that you have. Okay, so what about the disordered states? I'm going to get to it. The big Coulomb interactions do not go away with disorder. They're really determined by things on the atom. This is exactly where this dynamical mean field theory provides a systematic approach to doing things, and it's basically a theory that starts at high temperature. That may not be the way it's stated in all papers, but that's really the idea. So let's take a case that's really complicated, and I want to treat it in this general sense without any details. This is going to be vanadium oxide, Pt1. That's a famous case from the 1960s. The idea is you're plotting along a line, you find that there. That would be increasing pressure is what the experimentalists can do. But what that does is increase the bandwidth, so it decreases the ratio of the interaction to the bandwidth. So here I put these little designations that I've used U for the magnitude of the interaction, W for the magnitude of the bandwidth, and it's the ratio that's important for these problems. And I'll use the designations of AF and PM for paramagnetic and antiferromagnetic. And if we do the LDA plus U calculation, or just an ordinary LDA calculation on DFT, we would tend to find a antiferromagnetic insulator to a paramagnetic metal for this case, for the vanadium dioxide. And sometimes you don't even get this state, but that's the purpose of adding the U parameter to better quantify this transition from a metallic to an insulating state. What about, just take that off so it doesn't get in the way. Now let's go up in temperature. What do you expect to happen? Certainly, you still expect a metal insulator transition. And I should have asked you first. Okay. If you increase the temperature for a paramagnetic metal, do you ever expect phase transition to something else? The structure might have a phase transition, but would you ever expect it to become magnetic? Would you ever expect it to become an insulator? For good reasons. This is already not ordered, and you go up in temperature, and it's still not ordered. So basically, you expect nothing to happen along that line. If you go up starting with the antiferromagnetic insulating state, you do expect something to happen. What? Transition to a disordered state, right? And basically, you know from theory of phase transitions that you've got to have some kind of a curve that's like this. That would be a decreasing transition temperature, say with pressure, or as U decreases, right? And now I've written up here paramagnetic insulator because that is what you find in the vanadium dioxide. It's not guaranteed that this is what will always happen. But notice that now we have this metal and insulator. And we know this is insulating in the sense that if you do an electronic spectrum, it still looks like it has a gap. All these features look like there's a gap. So there should be a transition between these two states, or it could be a gradual transition. And this is exactly what Mott was talking about. Would you have a gradual transition from a metal to an insulator, or should it be a first order transition? I think you can't just prove that just by thinking, but you can think of it as an interesting question. And in this system, it's a first order transition I'll just go ahead and put up the critical point. And you can just imagine that you should go from insulator to metal, and there should be a critical point. So in fact, you can go around without going through a transition, but in addition, there can be a first order transition between an insulator and a metal, and this is basically what's called the Mott transition. So this is the bottom-up approach, and this is often called the Slater approach, working at low temperatures, and in which case the metal turns into an insulator at the same time that it becomes antiferromagnetic. Okay? let's go top down. We start up here as for metal, where it's metal, and you don't quite know whether it's going to turn into an insulator. But at some point of small enough U, it'll just be a nice metal. Okay? If you, up at high temperatures, it's going to become an insulator somewhere as U gets larger and larger. And this is exactly what Mike talked about. He proposed that if you pull the atoms apart, that would be going to low pressure, that at some point it'll always become an insulator, kind of independent of whether it's ordered or not. And now you know that if you have an insulator that's where the atoms are sort of decoupled from one another, and each one has a moment you know to order, and so you basically get exactly the same picture you had before, but starting from a different point. Okay, so how would one actually do that? There's an old idea that's been around in many, many contexts, is to look at an atom that has strong correlation on it and treat it as in a bath of the other atoms. Here's one case that you might know about from the textbooks. Bigner and Sykes, 1933 and 4, the alkali metals. Like first quantitative calculations. What did they do? They didn't worry about temperature at all, but they did something very clever like correlation. They proposed that in each sphere around an atom, there could be one electron, and the presence of one electron excludes the others. And that gave them a way of getting correlation quantitatively. And gives a simple expression for the Coulomb interaction energy. And it's really worked very well for the alkali metals. And the kinetic energy, the bandwidth, they just kept as basically free electrons. So that wasn't particularly modified. Okay? Here's going to be another case. In the 1960s, there is the cases that were now called strongly interacting. Blitzwiller and Hubbard were the two names that are most around. I should have said they just didn't worry about temperature. It's not that it was temperature to zero. They just didn't specify anything that had to do with temperature. And they applied it to open shell systems. And they included correlation in a clever way. They said each atom would be highly correlated, but they'd assume no correlation with the surrounding atoms. So but the key thing that would happen is that the kinetic energy, the bandwidth, would get decreased because an electron on this site would be its possibilities for hopping to neighboring sites is reduced by the fact that there may be a strong Coulomb repulsion for an electron on the neighboring site, depending on whether another electron is there or not. So just a very simple picture. So unlike the Wigner-Sykes idea, in these systems it made sense, and it was their brilliant approaches to say that the bandwidth gets reduced. And this allowed them to get to metal insulator transitions. Sorry if you can't see that. This is metal insulator transitions, and it's a bootstrap effect. As the kinetic energy and the bandwidth gets smaller and smaller, the system can go to an instability and go from a metal to an insulator. And here the Hubbard was kind of the cleanest way to think about it. It was like an alloy, and just like the same problem as an alloy, where you have two different kinds of atoms, and they can make a split band or one band, depending on whether they're very different or not. You use exactly that same idea. So dynamical mean field theory comes along, and it uses the same idea, but it really puts in temperature. Each atom is strongly correlated, and at first it's considered the neglect of correlation for surrounding atoms, which is valid at high temperatures, but then, So you still have this reduction of kinetic energy, and maybe I didn't put it in. It's supposed to say you then go ahead and try to put in the correlation with the surrounding atoms. That's down here. The thing that I didn't write down in any equations, but is the key thing to think about, is that a Green's function describes the one electron Green's function describes the ability for an electron to hop onto or off this site. And so if we look at the Green's function of this site, it's coupled to this path around it, and the one electron Green's function is telling you how this atom is in equilibrium with its neighbors. And it's a self-consistent problem, because if we take this as iron, for example, if this is an iron atom, then that's an iron atom. And they need to be equivalent, even though you're treating this one a particular way and these as bads. They need to be consistent with one another. So if it's a self-consistent Green's function, then you can have this bootstrap effect and get metal insulator transitions, phase transitions, describe magnetism. And this is what I'd like to mention then as we go along. So here's a picture of the electron excitations. Oh, I'm a little later than I thought. If you start with small interactions, then you get basically a band, and this would be the typical picture of a half-filled band. If you go to the bottom case, where you have a very large interaction, then you get this picture that modern vision is that you can have one electron in this lower band. It's called a Hubbard band, and if you want to put a second electron, then you have to pay the price of U, and so it has to go at much higher energy. And that's very logical. And in the middle, you get these multiple energy scales. And this is this Kondo effect. This is the interesting things that happen in many body systems, where you can get these low energy features that have a lot of that can vary a lot from one system to another, and interesting temperature dependence, while you still have this large energy scale. So that's the kind of thing that you can treat with this approach. Okay, so here's cerium. This is the case that was known a long time ago, and was just presumed that this very large effect that occurs in cerium had to do with a complete change in the character of the up electrons. There's a low volume phase and a high volume phase, and the volumes can differ by as much as 15%. That is a huge change for metals. Have any of you done phase transitions, like silicon melting, for example, or silicon under pressure goes to a metal? The volume change is not this big. Okay? And it's a first order transition between two states. That's a face-centered cubic metal, a face-centered cubic metal. And no change in any other symmetry. It's just that the volume collapses, is what it's called, a volume collapse transition. And it has a critical point. Here's the spectrum. This cerium, let's see if I've got it. Yeah, I can explain what this is. This is a spectrum as a function of the energy, and this is the Fermi energy here. Taking an electron out is measured by photoemission. Putting an electron in is essentially shooting in electrons and looking at the photons coming out, and you can call it inverse photoemission if you wish. And here's these two states that are the low volume and the high volume. The low volume one is this collapse state. I keep losing it right in here. There. Has this anomalous feature at the Fermi energy, even though this large energy scale is still present. The high volume case, this feature has either disappeared or gotten so small that you can't see it. And what it really means is so narrow that you can't see it. I'm not going to show you a picture of it, but there's some cerium compounds, like cerium aluminum 3, which has a feature near the Fermi energy that's like 10 Kelvin wide. Can't even be seen in photo emission, but it's there because you see it in specific heat. So just enormous changes can happen with these materials under different circumstances. And this is what's called Kondo peak. And this is the kind of thing that I would point you to a paper by Andy McMahon and coworkers that they did DMFT calculations, dynamical mean field theory, the self-consistent Green's functions, by getting the parameters from density functional, and they really did LDA. And from that, they were able to calculate the phase diagram and show that it was driven by entropy. Basically, it's the disordering of these moments as you go up in temperature. And they verified that this modeling called a Kondo volume collapse was actually true, that as shown by this electronic spectrum and by the theory. And this is like a Kondo temperature that's around 8,000 Kelvin, and it's enough to cause a 15% volume change. Different case. Let's do a good old magnet. Nichols example. Here's what you get if you do a cone-sham calculation. You make it spin polarized, and you find that's the lowest energy. That's the non-magnetic case where you don't allow spin polarization is higher energy. And just from the spin dependence in the local spin density approximation or spin density gradient approximation, you find that the one spin is more occupied than the other, and you actually get a pretty good estimate of the net moment. And if you do improved functionals and U values, then you can really justifiably make this seriously better. Okay, so what should happen if you raise this above the Curie temperature? It's not there's no net spin moment. What would you get out of a band calculation? Those would necessarily collapse on each other because one spin is just absolutely equivalent to another. The up is equivalent to down if it's not magnetically ordered. So this has been one of the criticisms from band theory. It says, it's rubbish. It doesn't give us the right picture at all on high temperatures, because you know these large energy scales of the exchange are basically come from the atom, and they don't go away. So all that goes away is the order, but the atoms are still pretty well like they were. And this is the result. I'd like to advertise this, not to say it's precise, but to say you've gotten the qualitative ideas very well. So this is iron and nickel, and I have to explain what these are. At low temperatures, it's ordered, and you calculate the moment, and you just know it has to have a curve, something like this. You just don't know where is the transition temperature. If it's local moments, well, if it's not local moments, then every aspect of magnetism goes away when you go above the Curie temperature. But if you still have those moments around the atoms, then they give rise to an enhanced susceptibility. And you learned about that in your textbooks, called Curie-Weiss law. And if you look from the right-hand side, you expect the Curie-Weiss susceptibility. So like the susceptibility is 1 over temperature minus the Curie temperature. So the inverse susceptibility, which is what this is, goes to 0. The susceptibility goes to infinity. And this is what comes out of calculations with a reasonable result for the magnitude of the susceptibility, which really is the magnitude of the local moments that are fluctuating. Okay, so starting from high temperature, you have a simple picture, just fluctuating moments, and the only thing about it is the value of the moments. That's the only thing you have to calculate. Okay, go down in temperature, the moments are becoming more correlated, and the some point they had the phase transition, and so this would be the approach coming from high temperature. And now the problem is to calculate the phase transition coming from high temperature. And these are calculations that use parameters from density functional. And so the qualitative success is the moments at high temperature and low temperature. What about the actual value of the transition temperature? In nickel, it just works out marvelously with reasonable values of U. And in iron, it doesn't. Way too high calculated transition temperature. Have any idea why nickel and iron might be different? I didn't. I get this from the experts in the field. It's basically that there's something that's not being taken into account well in iron that is much better in nickel. In iron, there are these long wavelength spin waves that contribute a lot to the fluctuations that decrease the Curie temperature, and the not so much in nickel. And these local pictures, where you're dealing with one atom and its surrounding neighbors, just doesn't take into account this long-range stuff. So you see that people starting for high temperatures have a way to go too. Okay, so coming out about right on time. Starting from high temperature or low temperature, the limits, small, very small interactions where it's band-like, and temperature is pretty unimportant for typical bandwidths, to large interactions where you have these atomic-like features, moments, because you have open shell systems, and all you have to consider is how they order. So that's relatively easy to treat. And it's the intermediate cases that are hard to treat, and I think that's why they go by the name strongly correlated. In fact, these cases with very large U are even more correlated on the atom, but they're less correlated between the atoms. And the cases called strongly correlated is where you have this mixture of large bandwidths, or I should say comparable bandwidths to the interaction. And so you have correlations on the atoms and between the atoms, and that's leading to multiple energy scales and great challenges in many systems. So the classic examples I'd like to leave you with are this vanadium dioxide. Okay? The reason I want to leave this with you is that it's not worked out yet. It's a beautiful picture. The picture was figured out in the 60s, but the trouble is that there's crystal field splittings for these atoms, for the electrons of the vanadium. There's distortions of the crystal structure, and there's just been enormous confusion about what drives what. And this, we're now getting to the quantitative point where this is, I think, being figured out. So this would be something to look for if we can quantitatively work out something that's actually very hard for the experimentalist to figure out why the phase diagram looks this way. And I can't resist putting up the last one. You all know this is not understood. The high temperature superconductors. So why do they form this